So we're gonna just work through some problems from chapters 3 and 4 from the Timberlake text. And so we'll start off with number 27. And so in 27, we are asked to basically fill in the rest of the table. So this is similar to one of your questions on your homework. And so for these types of questions, you want to really be able to use your periodic table. And so for the first row, it gives us the symbol of Al. So that's aluminum. All right, and so name of the element, we just write aluminum. And it's asking for the atomic number. So the atomic number are those numbers that are used to identify each element as a unique element and a unique atom. And so each element has a different atomic number. And so for aluminum, you'll find the Al, you find the number 13 as our atomic number. And for this isotope of aluminum, we have a mass number of 27. And so number of protons is equal to the number of the atomic number. So atomic number, same thing as the mass, the number of protons. So these two columns should be equal. So we have 13 protons. Number of neutrons. So if you remember, mass number is equal to number of protons plus number of neutrons. Okay, so if we're trying to solve for number of neutrons, we have our mass number, and we should be subtracting our number of protons to get neutrons. And so here we know that the mass number is 27, and that's equal to 13, which is our number of protons, our atomic number, plus our number of neutrons. And so here we subtract 13 on both sides, and we get 14 is equal to our number of neutrons. And for these questions, these are all just atoms. We're not dealing with any ions or any different charges. So our number of protons should be equal to the number of electrons. So these numbers should be working themselves out. So we have 13 protons, 13 positives. So we should have 13 electrons, 13 negatives. We'll do the next one. So it says we have an atomic number of 12. So we look on our periodic table. Okay, we look on our periodic table and we try to find the number 12. And so number 12 we find right here, magnesium. And so then we have the name of the element, magnesium. And our symbol for magnesium was Mg. It says our atomic number is 12, so that must mean our number of protons is 12. Because we have 12 protons and 12 positives, we need 12 negatives, or 12 electrons. And the last thing is mass number. So protons plus neutrons is equal to mass number. So we had 12 protons, 12 neutrons. 12 plus 12 is equal to 24. All right, and so that's kind of how you work through problems similar to that. The next question is 3.29. What are the numbers of protons, neutrons, and electrons in each of the following isotopes? And so we have, we can look at B and D. All right, it's kind of blurry here. So chromium, we have chromium with the 24 on the bottom and a 52 on the top. So protons, neutrons, electrons. All right, so we find chromium. Chromium has an atomic number of 24. So remember, atomic number is written on the bottom here. And so that's always going to be equal to the number of protons. So it's 24 protons. Because we have 24 protons, 24 positives, we need 24 negatives, 24 electrons. And then neutrons. All right, similar to what we did in the last question. Mass number is written here. And so mass number is protons plus neutrons. So we have to subtract our mass number, 52 minus 24, and we get a number of 28. All right. Another way you can, we'll just work on the next one. So bromine has an atomic number of 35. So our protons is 35, and then our electrons, since it's not an ion, is 35. It says our mass number is 81. So since it's written like 81, 35, Br, one way to just do the neutrons is just set it up as a subtraction problem, and you'd get 46 neutrons. So this is just another way you can solve it out. And then 31, write the atomic symbols for isotopes with the following. So in A, 15 protons, 16 neutrons. So here you have to use your periodic table. Like much of this chapter, it says 15 protons. So we find the number 15 as atomic number, which is equal to the number of protons. And we find phosphorus. So that is our symbol. All right. When we have 15 protons, that's the atomic number. That's written on bottom. And then the mass number is number on top. So it's 15 plus 16. (31). And that's how you'd write that out. For the next one, we have 35 protons. So we look here, try to find number 35. We find bromine as we had in the past. All right, so we have Br. We have 35 protons, atomic number. And then 35 plus 45 is equal to 80. So 80 goes on top. All right, we'll work a couple of these orbital questions. The number of orbitals in the 3D sublevel. And so the number of orbitals in a 3D sublevel, we can have, you can use that picture that in the book, but you should remember that the number of orbitals is going to be equal to 5. Number of sublevels in n equals 1. N equals 1. You're on the first energy level. On the bottom energy level, you can only have the 1s sublevel. Alright, so that's just equal to 1. Number of orbitals in the 6s sublevel. So s only can have one orbital. It's just the s orbital. So we can just do 1. And then orbitals in the n is equal to 3 energy level. So if we're n equals 3, we can have the 3s, the 3p, and the 3d. S has 1 orbital, the p has 3 orbitals, the d has 5 orbitals. And so we can have a total of 9 orbitals. Number 43. As for the maximum number of electrons in each of the following. So 3p orbital. So a 3p orbital, it's just asking, we can have 3 different 3p orbitals, but in one orbital we can only have a maximum of 2 electrons, and those 2 electrons must have opposite spin. Alright, so if it ever asks the maximum number of electrons in any orbital, it will always be 2. Now, if it asks for the 3p sublevel, well, the 3p sublevel has 3 orbitals, and each can have 2 electrons. So we can have a maximum of 6 electrons in the 3p sublevel. Alright, and so that's kind of how you work through problems like these. Alright, see that. Alright, so now it's asking to draw an orbital diagram for each of the following. So we'll start off with, we'll go with B, aluminum. We'll do aluminum. Alright, and so aluminum we find here on the periodic table. Aluminum is right here, has an atomic number of 13. So if it's an atom, it's got to have 13 electrons. Okay, 13 electrons. So, kind of just keep this, zoom out so we can kind of see everything in place. How I kind of work through it is, alright, we have our first energy level here. Alright, we have our 1s. So we're going to complete our 1s. Alright, we have a 1s. Then, using that periodic table, we have 2s. Right there. Then, periodic table, we have our 2p. There's our p block over here. Okay, so that's going to be 2p. We're on the second line, 2p. Then, we have to go through our 3s. And then lastly, that's where we're ending up. We end up in the P block, so we need to end up in the 3p. We have 13 electrons. We first fill it up singly, then we can double it up. Single, then double. That's 4. Single, 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 double, double, double. That brings it to 10. Single, double, it's 12. And then, last thing, 13. So that's 13 electrons. Remember that we kind of had something like this in the slides. I can put this on the Angel website. And so here you can kind of just see where you should be ending your, what's the last orbital you should be indicating in your elements for your orbital diagrams. Okay, so you can just kind of remember that. You're not ever going to be given that on the quiz or a test or anything like that, but you kind of just put that in your visual brains. We can do another one. We could do an easier one. We'll just try, since all the other ones are pretty much the same area, we can do boron. We'll do A. Boron, we find on our periodic table. Alright, boron, it's got an atomic number 5, so that means 5 protons. To be neutral, need 5 electrons. Alright, so boron's here, so we need to go from, we need to fill up our 1s, then it's going to go to the 2s, then we go to the 2p. And so single, double, single, double, single. And then that's about it. That's how you kind of work through these orbital diagrams. Okay. Now we're doing something similar. We're writing an electron configuration for each of these atoms. And so this is number 3.47. And so we can look at sodium. B. So sodium, Na. Alright, first thing you want to do is get your periodic table out, find sodium. Find sodium 11, so 11 protons. And so that means 11 electrons. Okay, and so the order, you go 1s, and you can have 2 electrons in the 1s. Then 2s. Okay, so you filled up your 1s level. Now you have your 2s. Go past that, 2s2. You have 2 electrons in 2s. And then you're going past all of the p block. So 2p6, you can have 6. All right, 1, 2, 3, 4, 5, 6. And then you end up with the sodium. So you have 1, 3s, because sodium is in the first group. Since it's the first group, they should always have 1 valence electron in the 3s. We do a little bit more difficult one. We can look at arsenic. So we look for arsenic. Arsenic has an atomic number of 33. So we got a few of them, 33 electrons. So you find arsenic, you have to go past the 1s. The 1s is complete. You complete the 2s. You complete the 2p. So 2p6, you can have 6 in that p. You fill up the 3s. You're going to fill up the 3p. Then you have to go past the 4s. And then you have to go past the D block, 3D. Alright, and there's 10 in that. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then arsenic is 1, 2, 3 into the 4p orbital. Okay? And so you're looking here, okay? Kind of going over the same thing. Arsenic is all the way down here. So we filled up our 1s. Then we filled up our 2s. And we filled up our 2p, second row, p block. Alright, we're in the third row, s block, 3s. And our 3p, our p block, we go past that block, 3p. 4s, we fill up. And then we have to fill up our 3d, our d block. And it's kind of offset. We go from 4s to 3d. But that's how it's done. And then we have a 4p here. So we have 3 electrons in the 4p. So it kind of gets tricky right here. You have to remember that the d orbitals are kind of one energy level offset from the period numbers. We'll look at 3.49. 3.49 is asking us to do something very similar, but we have to write the abbreviated electron configuration. And so the first one we'll look at is magnesium. All right, magnesium can be found right here with an atomic number of 12. So with the abbreviated version, what you have to do is you have to look for the last previous noble gas. And so it's just going to be the noble gas that's all the way on the right hand side, that's up 1 period. Okay, so if we go up 1 period and go all the way to the right, we find neon. So we go to neon, put neon in brackets, and then neon brought it all the way up to the 2p6, and so all we have left is 3s2. And so what's nice about using the abbreviated version is that it can really show the valence electrons easily, and so it can be very useful. We can do aluminum next. So aluminum, atomic number is 13. So again, we have to use the noble gas that's one period above it, which is still again neon. And so aluminum is found 1 over from magnesium. So you have to go 3s2 and then start your 3p block. 3s2, 3p1. And then that is complete for A and C. Here, for 51, you have to go in reverse, use these electron configurations to then figure out where you are, what atom is talking about. You can do this multiple ways. You can count over the, go through the electron configuration each, or you can just count the total number of electrons. So we can do both ways. So for A, it's 1s2. Can't see it. So 1s2, then 2s2, 2p6, 3s2, 3p4. And so you end up with sulfur. Okay. You could also just add up the total number of electrons. We have 2 plus 2, which is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. And 16 is an atomic number. Plus number of electrons, which should be equal to the number of protons, and that is the atomic number of 16, which is sulfur. Another thing you could do is just look at 3p4. That's your last valence orbital. And so 3, third row down, p, block, right there, 4. Fourth one over in the p block. Bring your sulfur. So you can do it a variety of ways. If you have the abbreviated version, alright, so if you know that you have, like in C, you have neon, then you have 3s2, and then 3p2, which would be silicon. Or if you just look at 3p2, the last thing, brings you to silicon. P block, third row, 2, second one in. So that one's very similar, just a lot less writing. Just going in the reverse direction. Okay, I skipped one. Okay. 59 says, write the group number and electron dot symbol for each element. So 359, write the group number and electron dot symbol. So remember, in the lecture it said that it's very convenient that this group 1, has 1 valence electron. Group 2 has 2 valence electrons. Group 13, or 3A, has 3 valence electrons. Group 14, or 4A, has 4 valence electrons. Group 5, or 15, or 5A, has 5 valence electrons. Group 16, or Group 6A, 6 valence electrons. Group 17, or 7A, 7 valence electrons. And group 18, or 8A, 8 valence electrons. So that's what we pretty much can do here. 59, we find sulfur. Part A, sulfur. Sulfur is right here in group 16, or group 6A, which means 6 valence electrons. So A is group 16, or 6A, whatever you would like to use. And then we have sulfur. So remember, you write 1, 2, 3, 4 dots around sulfur, and then you can start pairing up. 1, 2. Okay? So you have 2 paired electrons, 2 unpaired electrons. If we look for which one we want to do, we can do So we hit the max on the length of each video. I guess is 20 minutes. So here we'll just finish up with C and E. So C is calcium. Calcium is found in the second row, group 2, 2 valence electrons. Group 2. And so we have Ca calcium, 1, 2. All right. And the last one we can do is gallium. Gallium is group 13 or 3A, Ga right there. And so then E is group 13 or 3A, which means 3 valence electrons. So you put Ga, 1, 2, 3 dots around the Ga. Then the next section looked at periodic trends, so select the larger atom in each pair. So, a couple trends that you can try to remember is that if you look on the periodic table, this bottom corner will be the largest atoms. This top right corner is going to be the smallest atoms. Okay? And so, as you go down the periodic table, you're adding energy levels. Those energy levels are going to increase the distance away from the nucleus. Those electrons are getting further and further away. And as you go from the right hand side to the left hand side, you have electrons in the same, if you're as long as you're comparing on the same period, as you go from right to left, you have the electrons in the same energy level. The thing that's changing that's going to affect it the most is number of protons. And so you have more protons on the right hand side, so more positive protons are going to attract those electrons on the right hand side. You have less protons in the same energy and electrons in the same energy level, so you have less attraction with the left hand side. That's how I remember it anyway. And so on the left hand side you're going to be bigger, and then you're going to be bigger as you go down. So sodium and chlorine. Sodium is on the left hand side, chlorine is on the right hand side on the same period. So sodium, left hand side, you have electrons on the same energy level, but you have less protons. So sodium, Na, is going to be bigger. Then we can compare and sodium and rubidium. And so here, all right, we're going down the periodic table. So we are going down the periodic table. We have sodium and we have rubidium. And so there we have more energy levels. More energy levels. As you add energy levels, you're getting further away from the nucleus. And so rubidium is going to be bigger. Rb. And so next one, 63. Place the elements in each of the in decreasing order. Alright, and so we'll just do one of these. It's pretty much the same premise. Well, I guess we can do two of them. So Al, Si, and Mg. These are all magnesium, aluminum, silicon. They're all on the same period. So they go from smallest to largest. So Si, Al, Mg. So decreasing, all right, should be the smallest one at the end. Smallest one at the end is going to be Si. Si is going to be smaller than Al, and Al is going to be smaller than Mg. Then you can do the same thing for chlorine, bromine, iodine. So you're comparing along the same group. So as you go down the group, you're adding energy levels. They're getting further away from the nucleus. So Cl is going to be smallest, Br is going to be a little bit bigger, I is going to be the biggest, iodine. So the biggest one, or the smallest one, should be chlorine, then bromine, then iodine. Alright, next one, 65. Select the element in each pair with the higher ionization energy. So highest ionization energy. So if you remember from your notes, you have to remember where you would find the higher energy level. So you can kind of maybe, how I kind of do it is I kind of use my reasoning behind the radius and try to bring it in those terms. Okay? And so I got caught up again. I ran out of space on my camcorder, so I had to transfer everything. But going back to 65. So it's asking which element of these pairs is going to have the higher ionization energy. And so you want to remember that ionization energy is going to increase as you go up and over toward the right hand side of the periodic table. So if we go and look at a periodic table, if we go to the right hand side and as we go up, it's going to be greater in ionization energy. So it's going to, the way I remember that is that it's going to require more energy to make an ion, because you have the electrons closer to the radius, or closer to the nucleus, as you go up and to the right hand side of the periodic table. And so that's how I remember it. And so since the electrons are closer to the right, closer to the nucleus, as you go to the right, the atoms are getting smaller as you go to the right, and they're getting smaller as you go up. The electrons are closer to the nucleus on the right. As you go up, there's going to be more attraction, so you have to break that attraction some way, so it's going to require more energy. And so in 65, you can, for ionization energy, the ionization energy is going to be greater as you go up and to the right. The top right corner is going to be the highest energy, ionization energy, and as you go to the bottom left, it's going to be the lowest ionization energy. And so 65 and A, compare bromine and iodine. And so bromine, you have the electrons, the radius is going to be smaller. We have less energy levels, so those electrons are going to be closer to the nucleus. And so it's going to have a higher ionization energy. So bromine for 65 is going to have higher ionization energy. Then when we look at, B's is pretty much the same thing, silicon and phosphorus. All right, when we compare elements of the same period, silicon, phosphorus, we have elements in the same period. So remember, as you go from the left to the right hand side of the periodic table, so from the left hand side to the right hand side of the periodic table, the electrons are getting closer to the nucleus, so there's going to be greater attraction to the nucleus. So you're going to require more energy, and so phosphorus is going to be the one with the higher ionization energy. So we'll look at some in chapter 4. Chapter 4, we'll look at 4.3, looking at isotopes, or connects what we were talking about in the previous chapter with isotopes. So isotopes have, isotopes are atoms that have the same number of protons but different number of neutrons. And so this one goes over 3 different isotopes of potassium. So potassium is K, and so we have it says write the atomic symbol for each isotope. So K would be 39, and so 39 is going to be the mass number. And then when we look for potassium, or K, on the periodic table, we find it here has an atomic number of 19. So we do K and then 39, 19 for potassium 39. And so for isotopes, is going to have the same number of protons. So they're going to all have the same atomic number. And so the only thing that's going to change is the mass number. And mass number is written on top. Here, 4.5 is much of what like we did in the previous chapter, filling in this table. And so if we have the, just basically need to fill in the subatomic particles and number of each. So we'll be looking at thallium first, thallium 201, or let me double check. Let's see, kind of blurry on my paper. (201), and so the mass number is going to be that top number. So the top number is 201. Number of protons is the atomic number, always written on the bottom. So that's given to us as 81. And so to find number of neutrons, it's going to be 201 minus 81, which is equal to 120. The next one is we have some atom or some isotope being used for radiation therapy. So it says number of protons is 27. So right off the bat, we know that it's going to be, we'll use our periodic table, it's going to be cobalt. Cobalt has an atomic number of 27. And it has a mass number of 60. So that's how we would write our symbol. And then number of neutrons, it's going to be 60 minus 27, and we get 33 neutrons. And then the rest of that chart is done in the same way. 7, it says write the symbol for each of the following isotopes used in nuclear medicine. And so much of the same. So we'll look at copper 64. So we find copper. Copper is right here. We've got an atomic number of 29. So atomic number goes on bottom, and then we have the mass number on top, which is indicated by that number after the word copper. The next one asks us to identify each of the following in 4.9. So first we'll look at part number D, or letter D. So we have a mass number of 38 and an atomic number of 18. So we look at that bottom number. That bottom number is 18, and so we find argon with the atomic number of 18. So D would be argon. So that's the big thing, is you're using the symbols, using that atomic number to identify your element. So it would be argon, I guess, 38. Alright, and now we are asked to write a balanced nuclear equation for the alpha decay. So it's alpha decay. Alright, so alpha decay, you want to remember 4,2-He. And so we can do the polonium. We'll just do A. So we have polonium. It is, I believe, 208. Yep, 208, 84. And that's alpha decay. So we're going to be ending up with some question mark 4,2He. So first we can find our missing mass number. So 208 minus 4 is equal to 204. So we have 204. Then our missing atomic number is going to be 84 minus 2, which is equal to 82. So 82 is our atomic number. Then we must go on to our periodic table and find number 82. And we find it as Pb, or lead. And there you go. For number 15, it's asking us to write a balanced nuclear equation for beta decay. So beta decay. So remember, beta 0 minus 1 E. It's going to have a high energy electron getting out of there. And so we'll do iron 60. So Fe is iron. 60 is representing the mass number, and then we go on our periodic table and find the atomic number of 26. We're going to be losing that beta particle. And so mass number is going to be 60. 60 on both sides. So we're not changing the mass number. And then for the atomic number, it's going to be 26 and then plus 1, which is 27. So 27. Alright, and then 27. Alright, because 27 minus 1 would be 26, which would be equal to that 26. And so 27, we go on a periodic table, and we find 27 on the periodic table, and it's cobalt. Cobalt. So it's cobalt 60. And so here, on number 19, complete each of the following equations and describe the type of radiation. We'll do one of these, and we will do, I guess we can do two. We'll do C and D. So C, we have Cu, we got 66 and 29. And that is degrading to zinc 66 and 30. Plus question mark. So much of the same. So we see the same number here, so that means the top is going to be a 0. And then 29 minus 30 is equal to -1. So minus 1, and that would be the symbol for the beta particle. So it is going to be beta decay for C. Then for part B, we have something going to thallium 234, which has an atomic number of 9. And so this is a beta decay. And so here you just have to make sure that we have everything already on one side, so that has to equal the mass numbers on the right need to equal the mass numbers on the left. So 234 plus 4 is equal to 238. Then the atomic numbers need to add up, so 90 plus 2 is equal to 92. So we have 238, 92. And then we go on a periodic table and find 92, and we find uranium 238. So just make sure you balance out the mass numbers and atomic numbers on both sides of the equation. And 21. It says complete each of the following bombardment reactions. So we have we'll do part we'll do B. So we have 1, 0, neutron, uranium, what's that, 131. Yes. 131, 52. And then question mark, and then you are releasing a beta particle. So 1 plus 131 must equal x plus 0 for our mass number. So balance out our mass number. So 132 is equal to x. Then for the atomic number, we have 0 plus 52 is equal to x minus 1. So 52 is equal to x minus 1. So 53 is equal to x. So that means we have 132, we got 53. We go on the periodic table, look for number 53, you find iodine. And there we go. And so you just put in that into our equation, and that is the complete nuclear bombardment reaction. So hopefully this video helped clarify any confusion in working out these equations and problems. If you have any questions, just ask during lab.